Now let us see the physical properties of these elements. What we find in the physical properties is that all of these are, we can call as, they all are solids, they all are typical metals. Typical metal means what? I want to say that we can't say sodium or alkalis to be typical metals. We can't say aluminium or boron family to be of typical metals. Typical metal means all those elements, they are the elements which shows all typical behavior of very good metals, like they are very hard, strong, tough, malleable, ductile, lustrous, sonorous, etc. All such strong, good, typical properties of a good metal are shown by these elements. They are having very high melting points, they are very good malleable, they are very much malleable, ductile, lustrous, they all are very hard, strong, and that mainly is because of their very strong metallic bonds. Because of very strong metallic bonds. See, their metallic bonds are strong because they can contribute more number of electrons per atom. Those delocalized electrons, as we have seen in the case of the electron C model, so the number of electrons contributed by per atom are more in these cases. That's why what we find is they get more delocalization of these electrons is there. They get what stronger the forces of attractions are there between the electrons and the metal kernels, and that's why their metallic bonds are very, very strong, and that's why they show the typical metallic characters of their typical metals. We can show that this property of strong metallic bonds by a property which is called enthalpy of atomization. We write its symbol as like this, atomization, or we simply put A here. That's called enthalpy of atomization. Now see, they all have very high enthalpies of atomization. The reason is because they have very, very strong metallic bonds. That's why this is being proved by the atomization. So it's energy required to convert one atom or 1 mole of the atom present in the solid state to the gaseous state. So that's why this is a parameter which tells us that all of these are very good, very typical metals. Another important thing to note about these transition elements is that the 4D and 5D series elements are having higher values of enthalpies of atomization than 3D. So that means they are much more typical metals than the 3D series element. The reason is because of their smaller atomic sizes, higher nuclear charges, higher charge density. As a result, they are having much stronger metallic bonds. That's why they are actually more typical metals than the usual 3D ones. But all of these, exactly in a common language, we can say that they all are very good typical metals in that way. Let us see the next property, which is their atomic and ionic sizes. See, what we find is, and we know along a period or in any one of these series, what we find is the atomic size decreases along the series, and that's pretty obvious because the electrons are added to the same subshell and the nuclear charge keeps on increasing. That's why what we find is that the atomic size decreases along the series. So along the period it decreases. But what we find is this decrease is not very significant. Scandium, titanium, vanadium, chromium, manganese, iron. Let me write down in this one line. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. What we find is the size decreases fine to the middle of this, and then it becomes almost constant in these three elements, and then it again picks up in case of copper and zinc. Now it becomes almost same in these three elements in the second half of the series. The reason is because the number of electrons, of course, what we find is due to the pairing are getting decreased. So that's why what we find is the interelectronic repulsions and the increase in the nuclear charge, they counterbalances each other, and that's why the sizes are almost comparable. But the moment we get 3d10 configuration in case of copper and zinc, due to the stronger interelectronic repulsion, the size increases. And the same trend is noticed in the lower cases. But what is most interesting to note is that the radius of 4D series elements, when compared with the radius of 3D series elements, what we find is the 4D ones are having larger sizes, obviously because they get screened by the inner electrons. But since the 3D electrons are most poorly screened, remember, they all are having very, very small atomic sizes because 3D electrons are most poorly screened. Then when we compare the radius of 5D series elements with the radius of 4D series elements, what we find is their sizes are almost comparable. The reason is because of the poor screening of 5D electrons. 5D electrons are very poorly screened. Why? Because of lanthanide contraction, because of the 4F. That's because 4F electrons are very poorly screened. It gets lanthanide, that shows lanthanide contraction, due to which the 5D electrons gets also very poorly screened. That's why what we find is the last two series are having very similar atomic sizes. So in general, what we say that all of these 30 elements are having almost similar atomic sizes. That is why they can be mixed together very easily. They can exchange their lattice positions, and that's why they can be combined to form different types of alloys. So that these are the basic trend what we find in the atomic sizes. Ionic trend also shows when they are taken in the same oxidation state. Ionic trend is also exactly very similar to the atomic trend.